Hello everyone, my name is Mohammed and this is my third progress video for my computer technology part 1. Uh, and let's just get into it. Alright, so the technical work completed is I've finished my overall design and I've kind of figured out what peripherals I want and what future like peripherals I would need to actually expand this and upgrade the motorcycle circuit even further. So, the first bit is I wanted the ESP controller or the ESP processor to control nothing. So the ESP will have most of its pins connected to the FPGA to communicate in like different formats. So like I can make it communicate in I2C, CAN, UART. It depends on what exact peripherals I choose, because some peripherals will like one protocol over the other, and yada yada yada. Yeah, and then I want the FPGA to control everything else. So I thought of a memory module would be nice to hold and the debug signals, be able to export it, and to actually store the tune map itself. So that would be the lookup table of what timing happens at, so what I'm measuring, which is the timing coming in, and when the spark what is the delay for that spark before it gets sent out. So that will be held in the memory module, and I would have a a circular buffer to actually load in the next 10 and the previous 10. And if my revs goes up, I will drop one and then I'll load in the next one. And just be continuous talking between my memory or RAM chip into my FPGA. Now, I thought it would be nice to have an IMU to actually detect the angle of the motorcycle and add it to an ESP, which can make a Wi-Fi signal and connect to it. Make a simple website to debug all of this. And uh, and then the next thing I thought about is using the ESP Wi-Fi to be able to dynamically reprogram my FPGA chip or dynamically reprogram my ESP by having two dedicated ESP, well, one ESP programmer chip, one FPGA programmer chip, rather than like having it external to have it all nice in a single dev board. All right, now there are some problems that I've faced, and that's why I wanted to speak to a engineer that does this professionally. Recently, I got a new job at a company which they are technical, and thank God that they had a bunch of PCB designers and firmware engineers. As I was showing him kind of my full circuit and what I was thinking, and he explained to me what are rules of thumbs and how I can protect it even better. So the these are different circuits of to protect pins, but I'll go back to my previous slide to actually explain why I would need to protect pins. So currently, this side of this is a PNP transistor acting as a switch, and the FPGA will send a signal to base. Well, the base when it's high, it will activate the circuit, making the VCC, the unregulated voltage, go through the transistor and out to the spark plug. Now, there's a problem that I've observed, but I didn't know how to describe or look up. So the problem that I noticed was if I noticed it when I was creating NE555 timers before, where my I would burn out the NE555 timer pinout, and I wouldn't understand why. It turns out, um, as a signal is getting sent to the base of the transistor, the voltage and current will come through here, go through here, and back to the spark plug. No problem when it goes on, but when it turns off, what it would do is it would send the signal back, and there is a small like window where instead of it sending it back, going back to the high side, it would see that this is low, and we all know voltage goes to the voltage difference. So it will go back down, and because this one just recently went off, it would send a huge amount of voltage and current, bending out that pin. And that's the part I didn't know how to fix or how to describe or what to look for. So, where after I asked him, he explained to me there are four main different types of circuits to actually like fix this problem and protect the actual processing chip of it. So we have we have something like this, which is called a load switch. There's a lot of designs out there made from Texas Instruments, and these load switches, all they do is they get a low signal, they isolates it, and then a controller and then sends the same signal to the transistor or whatever to actually send it to the to actually turn on or off the signal itself. And you generally, he said, load switches are the best kind of use case, but all these other ones also would work. So we have this one, which is called an optocoupler, and this one is also nice, where it's an IC chip where it's completely isolated. There are no connection between this diode and this transistor, and the way it works is the microcontroller would make this go high, making this active, or like making some light, or to for that would affect something completely this other circuit that would turn on, and then from that it can isolate the same signal. It would still be low voltage, but it would be isolated. That's the main bit, and it would actually activate. In my design, it would activate the transistor, activating the high voltage. So that's called an optocoupler. The other one is called a snubber circuit. These are generally used for DC motors, because what can happen is as you're driving the DC motor really fast, when you turn off it, the DC motor keeps on spinning, generating electricity and sending it back the way it came in, which can damage the pin as well. So generally, what people would do is they would add a diode and a resistor to actually protect it, a capacitor to smooth everything out. And the final one is called a snubber circuit, or a snubber circuit, where it uses MOSFETs to actually control everything. It's they all complete the same thing, but I'm assuming at different degrees. So this is kind of my next stage, is to actually learn all of those. Whoops. Hello. That's kind of my next step, is to learn all of those, the difference, and which one is the best for my implementation. And what do I need a combination of them to actually control it? I don't think I would need this one, but I'm still learning about it, because that's why I kind of spoke to a firmware engineer, so I know the stuff that I'm missing. Yeah. Um, he also told me about different programming boards, logic boards, and he told me about um, these other brands that sells high voltage, high current microcontrol chips, which I had no clue that there are boards out there like that. But anyway, I've chosen my design and I want to continue with it and finish it. All right. So what is next? So the next bit of this is to actually finish building my circuit. So I've tested each bit of so I've tested my power networks. I've tested my FPGA. I've tested my ESP controller, but now I need to put everything together and have a little prototype. And the next milestone is actually finishing the design and ordering it from PCBWay or one of the other many PCB manufacturing services that are out there. Now, that's one part of it. The other part the other milestone that I need to do is actually figure out how to make my board dynamic, because I still want it to be extendable. I don't want to use just 3 or 4 pins. I want to use the whole range of pins. So I want to see what is the best division to actually control more peripherals, because the stuff that I want to do after this project that might take me a little bit longer is fuel injection. So I'm not going to convert the motorcycle to fuel injection yet, but that would be kind of my next step after uni. Uh, and I'd rather have create the board now and create the code later, basically. And I want to also add more like modernize it. A lot of the motorcycle signals are analog. I Analog is nice, but the problem is they stopped selling replacement parts. So if any of the analog pieces break, I'm either there recreating the analog pieces or modernizing it anyway. So I want to use the rest of the, like, I think it was 100 pins into making a dynamic module or a dynamic dev board, basically. That's kind of my goal. And learning about all these circuits, how can I integrate it with this little piece of circuit here, over here, and what is the best, safest configuration to keep everything safe. The other milestone, but I was told by a different engineer that was a little bit easier to implement, was dynamic reprogramming of the ESP and the FPGA. They said usually the data sheet will allow you to write it in the NVRAM while it's running, and if anything happens, if anything wrong goes during the programming of the dynamic programming, it will just roll back to the original. And I want to learn how to do that. So these are the next 3 milestones. I think I have till the end of June to submit my design to actually get it ready for the next semester. Really excited to actually get this project live and happening. And yeah, this is my final video for the semester. I'll see you guys next semester.